Welcome to Study Loop.
Okay, so for this problem, which is problem 58 in chapter 40 of University Physics with Modern Physics, 12th edition, we are looking at the WKB approximation. And specifically with the WKB approximation, we are looking at the integral from one point to another point within a potential over the square root of twice the mass times the difference between the current energy and the potential energy. And this is an integral over the distance. And in the WKB approximation, we can say that this is equal to NH divided by 2, where n is an integer. And a couple relationships we're going to use at some point in this problem are that h is equal to 2 pi times h bar, and also that k is equal to m omega squared. And this comes from omega being equal to square root from springs and spring systems. So the first part of this question asks us to look at the classical turning points. And remember, the classical turning points are when E is equal to U. When there's no more potential for the system to continue moving, it's going to turn around. Think about a ball rolling up a hill, and once its kinetic energy at the bottom is equal to its potential energy, it will stop and turn around and fall back down. In the case of a harmonic oscillator, we're looking at the potential 1/2 kx squared. It's just the spring potential. And we would like to know that when E is equal to this quantity, what is x going to be? And it's easy to multiply both sides by 2 over k and get that x squared is equal to 2e divided by k. And therefore, the turning points, the classical turning points of this system are x is equal to the plus or minus square root of 2e over k. Part B is having us use these endpoints as our a and b in the system. And so I'm going to rewrite our integral now. Instead of the integral from a to b, we can do the integral from negative a to a, because b and a have the same magnitude overall, of the square root of 2m times now the difference between e and our 1/2 k x squared number. And that is an integral dx. Simplifying things further, we know that the integral over an even function, and remember x squared here is what we're looking at, is the even part. You can take the integral from negative a and turn that into twice the integral from 0 to a of the square root of e minus 1/2 k x squared dx. And again, that is the square root of this. Okay, so we're going to simplify the inside of the integrand now and say that this is equal to the integral of twice 0 to a of the square root of 2me minus mk, because the 2's canceled, x squared. and that is an integral over x. Okay, now if you remember from the standard integrals that one learns in an introductory calculus class, you can perform what's called a trigonometric substitution, but you can integrate something that has the form a squared minus x squared over an interval x dx. And you'll wind up with 1/2 times quantity x times the square root of a squared minus x squared plus a squared times the inverse sine of x over the magnitude of a and quantity. We're going to use this standard integral in this problem. And to do so, that means we simply need to rewrite our integral on the left-hand side as something that's resembling the integral on the right-hand side. You'll notice that it already looks pretty similar. We simply need to get x squared by itself. And we can do this by factoring out the square root of mk. And then we'll have the integral from 0 to a of the square root. And now we're going to say 2me divided by mk. The m's are going to cancel. And we will wind up with 2e over k, a familiar quantity, minus x squared. Yeah, we're taking the integral over this, dx. Okay, so now we can simply plug this in to our standard integral we're using, and we will get our 2 square root of mk from out front, our prefactor, multiplied by 1/2 times the quantity of x times the square root of a squared. Now remember, a squared was 2e over k as part of our substitution. 2e over k is in the same spot as the a squared in our standard integral, and so we are going to plug that in. 2e over k minus x squared plus 2e over k times the inverse sine of x over the square root of 2e over k. Now remember, the bounds of our integrand were from 0 to a, and that a quantity was our classical turning point. So we are now going to plug those bounds in. I'll actually write the classical turning point, square root of 2e over k. So now, when we plug this in, we will obtain 2 square root mk divided by 2 from the 1/2. So this 2 is actually going to go away because here and here cancel. And we will obtain the difference between x, which is now square root 2e over k, times the quantity of 2e over k minus 2e over k, which is 0, plus 2e over k times the inverse sine of the square root of 2e over k divided by the square root of 2e over k, which is 1. Now we take that minus. Remember, this is just a standard plugging in the bounds of an integral in calculus. Plugging in 0 for x, now we'll obtain 0 times a quantity, which we don't really care about because it's multiplied by 0, so it will go away, plus 2e over k times the inverse sine of 0 divided by something, which is just 0. Okay, so now that means that this one's going to go away, this one's going to go away, and the inverse sine of 0 is asking what angle do we plug in to obtain 0. which is 0. So this is also going to go away. And we are left with square root of mk times 2e over k sine of 1, which is what angle do we plug in to obtain 1, and that is in radians, pi over 2. And this quantity is equal to, from the very beginning of the problem, nh divided by 2. So nh divided by 2, and instead of h, we're going to write 2 pi h bar. And that was one of our relations that we used before, 2 pi h bar. Okay, so let's simplify this a little bit. We're going to be able to say that these 2's are going to go away. These 2's are going to go away. And we're going to have the pi's cancel on either side. And we can simplify square root of k divided by k. That's what I'm going to do in this term. We have the square root of m. And then the square root of k divided by k is actually just the square root of k in the denominator, or 1 over the square root of k. So we'll make that 1 radical, because we'll see why in a second, times e, which is equal to n h bar. Remember, square root of m over k. So up top, we used that omega was the square root of k over m, which means that this quantity is actually just 1 over omega. So now we have e over omega is equal to n h bar, or that e goes as n h bar omega. And thus, part B, we have shown that the integral from the WKB approximation is going to give us E scaling with n h bar omega. Now, part C is having us look at our equation we obtained and compare it to the equation from the textbook for the actual energies of the harmonic oscillator, which is n plus 1/2 h bar omega. And it's saying, is our equation we obtained giving us an overestimate or an underestimate? And if you plug in any value of n, the easiest one is 0, we will see that our equation tells us that, so for the case n equals 0, telling us that our ground state is going to be 0, or 0 times h bar omega, which is just 0, versus what the book gives us, which would be 1/2 h bar omega. And 0 is less than 1/2 h bar omega, so our equation is going to give us an underestimate. And that is how to do this problem.